DQ networks. It will be presented by Liang Go of Visa Research, and he also did a great job in helping organize the VDS workshop, which I'm very thankful. The room is yours.
Okay, thank you for the introduction. So, good morning, everyone. My name is Liang from Visa Research. So, I'm honored to present our work, DQNViz, here. I will try my best to entertain you guys, so you guys won't miss the lunch very much. This is a joint work between Ohio State University and Visa Research. Unfortunately, the key contributor, Pimpong, can't be here. Let's do not blame German government. Let's blame Trump because of this US visa issue. So I guess we all here have heard the story of AlphaGo. So basically, it's the first computer program to beat professional human players in Go game. And this demonstrated the power of deep reinforcement learning, and sometimes it can achieve superhuman intelligence. So then, what is the DQN? So the DQN actually is a popular deep reinforcement learning model. It proposed by DeepMind, and also it shows great performance over a lot of Arita games, as I show here on the screen. So you may be wondering now how a DQN play a game. So let's look at a breakout game. So a typical setup is like you have like a two-component, the environment, the action. The environment is a game, the action is our program. And then the agent will interact with the environment to maximize a certain goal. So basically, they were based on their current intelligence to say, okay, what kind of action I can move? I should move, like move left and move right, and then also fire the ball. And then and then the environment will update the state, which actually just is the image of the screen. So indicate the position of the ball, the position of the paddle, and also give the rewards, the feedback to the agent. It's like different points, 1, 4, 7, depends on which part you hit. And then the agent get all this kind of data, will adjust his playing strategy in next round. So the key here is how the agent makes the decision to move, right? So the trick is called a Q function. So basically, give a state, which is the image of the screen, and then given by the action, the function need to estimate the quality value, which is R. So let's look at this formula. So basically, giving you S and A, you give me estimation of R. Trust me, this is the only formula in my slides, and it's quite simple, right? Oops, I forgot to remove this from the slides, but let's just safely skip this, and then you can still understand my talk. So let's go back to the simple formula. So you may wonder, what is the deep part? Okay, the problem for this Q function is the S and A, the space is so huge. You cannot approximate this function very simply. So people are very smart. They say, okay, why not we just use deep learning to approximate? Because technically, if you have a complicated deep learning model, basically you can approximate any function, right? So that's what they did. So basically, you have a couple of image, as I mentioned, as a state. And then you have some action, which is move left, right, fire the ball. And then use the neural nets to make the prediction, to say, okay, to the estimate, okay, what kind of rewards I can have. And then the agents pick the best one, right? Maximize the total gain of the rewards. So that's how DQN network works. So it looks very straightforward, right? And also it's like magical because, as you know, deep learning right now can do everything. But wait, let me throw this question to you. Can you guess how many games we need to train a fairly good breakout agent? And how many hours with my little laptop? Just a bold answer. 1, 2, 3. Okay. so usually we need, so for very good one, we need 20 minutes of games. And with my laptop, it's around 30 hours. So here comes the challenges. So first, for the model understanding, it's a long, complicated process, right? It's not clear what kind of strategy the agent learned and how those strategies are learned. And of course, we don't want to stop it over there. Once they can improve the model, right? So it's non-trivial task to tune this model, tune the parameters to get a better model. So we also try to solve this kind of problem. So by targeting this kind of challenges, we designed this DQNViz tool. So basically, for the model understanding, we try to provide the training, this kind of view summarization of the training status, and also provide this strategy pattern, linear approach, and also understand this kind of strategy how learned through the nuance lens. With that, we also try attempt to optimize the model by optimizing the random action based on this kind of pattern we detect. And then let's move to the details. So first, model understanding. Before we understand the model, we need to understand the data space. So if you recall, the setup of the breakout game is like this. We have a sequence of the data, states, action, and rewards, right? And then the action is like we number it as 1, 2, 3, 4, as a moving left, moving left. And then also for the states, we just have a couple of a bunch of images. For the rewards, as you can see here, is just different points. When you hit the first layer, it's 1 point. First 2 layers, 2 points. Sorry, 1, 4, 7 points. So basically, the data is look like this. We have an action sequence, state sequence, and the reward sequence. And then we move to our design space. For given a sequence of actions, how are we going to encode them? So from the game start to the game end, we call it one axle. And then we first just visualize as a set of dots, and then with a different color indicate a different kind of action. And then for the second step, we connect this kind of same consecutive actions. And then we also indicate, encode the position of the pattern vertically to this view, to the y-axis. The x-axis is actually reflects the time, right? And then finally, we add this kind of background bar to show some action with associated with special points, like random actions. And then when you click a certain circle on in the view, you can replay the video, how the agent played it. And then let's look at this view in action. Let me see whether it's playing. Okay, it's playing. So basically, each row is one axle. So this is for one training epoch. You have multiple rows, and then you can sort them based on the rewards or based on just the steps. And then also we can zoom in, zoom out to look at the details. And so it's zoom in. And also we can bring up other additional information like the rewards or random actions. And when you click certain point, they just replay how the agent at this point to play the game. So that's pretty much how we design this part. This is a key part to understand this kind of pattern. And then we also introduce some pattern mining approach. First, to tackle the scalability problem, we have hierarchical clustering to cluster the different segments. And then we also use regular expression-based this kind of pattern mining technique. And then basically you can mine different pattern or strategy the agent was taking. I'm not going into the details of this technique, but I do want to show you some interesting movement pattern or strategy the agent learned through the training. The first one is digging pattern. So on the top of the row is the action sequence identified by our approach, and then I can play with this guy. You can see, okay, the agent is very smart. He just very precisely dig a hole through this, and then just every time just hit the same spot to dig a tunnel. So what's the purpose for this? And then the purpose actually is to get more points, right? So basically, following up of that, the agent just push the ball through the tunnel to just hit the top 2 rows, because the top 2 rows get more points. That's how the agent to get a lot of points. Those are very good strategy the agent learned. This is astonishing because human cannot control this kind of precision just to do the same stuff here. But on the other hand, we also observe some very bad movement. So for example, the first one is we call hesitating. So the agent just keep moving left and right, and get no point. They don't know how to jump this kind of loop, right? And then another one is we call is repeating. So basically the agent just keep moving the pattern to the left, and then even it already reached the wall of the game, the agent doesn't know, right? So this kind of 2 patterns are bad examples. And a follow-up question is how the agent learned. So we visualize the neurons activations. So basically it's a very simple visualization. You just use a bar to visualize the level of activations, and then the colors indicate the different neurons from different layers. As we can see, the layers from top get more activation from more deeper layer. And then we cluster them. We found that actually the different clusters actually take different responsibility. For example, this red cluster, look at the right part of the screen, and the green cluster of the neuron, look at the left part. So that's this kind of different neuron, they have a different responsibility to pay attention to a different part, right? That's quite amazing. And we also have some other cases to show, okay, the neurons actually how to evolve over time. So with this kind of understanding, we want to say, okay, how can you improve the model, right? So as we say before, where the agent failed, we have the hesitating, repeating pattern, right? And even worse case is when the repeating unit is very long, it's hard to detect. And then at this time it becomes a deadlock. Because the agent is repeat to do this, because every time they get the same image, they do the same prediction. They just do this exactly the same loop, and then this crash the game. This is deadlock. So we want to jump out of this. So how are we going to resolve this? Use random action, very simple. So the original idea is okay, we have the DQN, we just do the prediction, you move right at this time, and then we just introduce some random action. Say, this time we try not to not use the prediction, just randomly move left. And originally, the Verena implementation just introduced a fixed random action, like 5% of chance of probability you get a random action. But based on our observation from before the pattern detection, we see this kind of good patterns and bad patterns, right? So we think that's not efficient. What we want to do is based on the pattern, right? So we introduce this kind of pattern detect-based action random. So basically, if we see some bad movement, we increase the random actions. That's just a very simple improvement, right? So with that, we did some experiment and to validate our method. So the 2 baseline is the random action with 5% probability and also 2% probability. And then compare with the 5% probability, we have more rewards, the total points. But if you look at the random actions, actually we are significantly less. And also we have less episodes, means we have less life loss. If we compare with the 2% of fixed rate, we have pretty roughly same random steps, but the total rewards is much, much higher. So this demonstrates just a little bit improvement based on our understanding, our humans' input, and this kind of visualization, this approach build a human in the loop for the first survey. So we make a little bit improvement on this, but you can see the results, right? So with that, I'm going to conclude this talk. So basically we propose a tool which we call the DQNViz, try to help us understand the DQN model, and also we improve the model a little bit by optimize the random action and then with a different kind of features. And as for the model optimization, there is a huge space we can work on, like the experience replay, this kind of memory of the agent, how to optimize it. And we have to work with you guys to explore this area. As for we were talking about the collaboration, this is Streamlit plugin we're hiring. If you are interested in visualization, deep learning, and also in finance domain, we have different levels of opening. We need research interns and different levels of research scientists. And even we are hiring a research director, you need to talk to my boss, my boss, okay? And with that, thank you all for your attention. And I also want to thank my all collaborators. And now I'm happy to take any questions.
Thanks for a great talk. Please state your name and affiliation. Thanks.
Also, my from front of IGV, this is really great work. Everything about games, I like that very much. Some games, like Real Life, pay their reward only very, very long term in the future. Sometimes even only at the end of the game. Can you elaborate on a bit how those instance gratification or long-term gratification affect the learning rate or the complexity of the algorithms of those games?
So your question is how the long-term rewards can impact like the learning rate or learning strategy, right?
Yeah, you get instant reward depending on state, and this of course is a feedback from the universe. And if you can get this feedback in short term.
So basically the DQN, they have like two sub networks. So one is they call the target network, or another one is a current network. So the target network actually, they can, because not every movement you have to get the points, right? But the trick is like the target network can actually trace it back. Once you get a point, they can trace it back and say, okay, they can memory, okay, this is the kind of experience they have. And the current network, they keep playing. And playing certain rounds, and then they update the target network. So there are like two sub-network. And also another component I didn't introduce here is they have a very important component. It's called I mean intentionally didn't want to mention this. It's called the experience replay memory. So they already have a lot of experience stored in that memory, and every time they just randomly select some of this and to do this kind of training. So in that way, you don't look at it just the next actions rewards, but you also randomly select some past experience. Yeah.
Hi, Peter Ruch, Johannes Kepler, University Links. Very awesome work, but I was wondering how would you handle larger action spaces, because your visual encoding for the pattern mining you only have four actions. How would you handle, for example, 5 or 6, 7? I mean, you could change the color, but it wouldn't easily clutter probably. Did you look into this?
Yeah, I think that's a good question. So for example, if it's a Go game, how I can visualize this kind of different like actions, right? Yes, you're right. So that is one limitation, I think, so current approach. But I would just say, like, for now, even for the DQN, when the action space is just to be huge, it's hard to like train very stable model. And for us, we need to think about how to encode this kind of action space, right? Maybe you have we can introduce other visual encoding, or even do some dimension reduction, but that need further exploration. But the idea here is to say, okay, how we can understand the process, and then whether humans' knowledge or some simple pattern detector can help the model training. I think that's the take-home message.
Yeah, I mean, it would be also very interesting in terms of your rate evaluation, where you just then looked into the exploration aspect of the network by adding the random chance. Because if you have larger action spaces, just simple random exploration won't work anymore, because the space gets so much larger. And exactly for these types of problems, this pattern-based approach would be really interesting and really awesome. Can we try it somewhere? So do we have it on GitHub, or?
So right now we don't have it in the GitHub, but yeah, we are going to have the project and the whole source open.
Awesome.
Thank you.
Thank you.
There is Para from Catholic University in Chile. Two questions. One is, I didn't get if when you say that you were able to improve the model thanks to the pattern detection, you improve only the final reward, or you also were able to decrease the time for training, because at the beginning you mentioned you had to train for 30 hours, all these resources. Were you able then to reduce that?
Yeah, that's a good question. So basically, let me show you here. So basically, our approach is not only reduce get the total rewards. If you can see, the random steps actually significantly reduced. That can speed up the training. And also, if there is a deadlock, and then the game just crashes. So the training have to just stop over there and again, and then the game crash, and then start again. So that wastes a lot of time. So this one, we didn't do any regular experiment to say, okay, how much time we can save, but this is run the results over 10 rounds, right? So we just run 10 games to see what kind of results we have.
Okay, and one quick question more regarding the visual interface.
Yes.
If you would have a reward that change over time, which are dynamic, do you think your visualization should have to change too much, or as it is, it would work anyway?
So you mean the summarization part, or the encode, the actually trajectory, the epoch encoding part?
I mean that in this case you have fixed rewards.
Yes.
And the rewards might be changing over time.
Yeah, this slide shows what we did. So actually, this we have the interface summarize the changes of the rewards, Q values, and the life loss, and a number of games, this kind of stuff. But I didn't have time to show that. And also, even you can customize what kind of measure you want to have. For example, the bouncing. So you define this kind of pattern, and then the system automatically generates the patterns, the curve, saying, okay, how much pattern you have over time. Once you see there's jump of this pattern or a drop of this pattern, there has to be some problem, and then you can dig into what's the problem, what kind of situation the agent was stuck, and then you can design more mechanism to improve your training.
Okay, thank you.
All right, let's